Hello, I'm Haorian Mo from Sun Yat-sen University. I will talk about our work on vector line art generation. This is a collaboration among Sun Yat-sen University, Waseda University, and Huawei Technologies Canada. First, I will talk about the background. Vector line art plays an important role in graphic design. For example, in engineering design, the architectural floor plans should be cleaned up and stored with vector primitives for further design. In the field of 2D animation, the input line drawing is required to be represented as vector graphics. Vector line arts also aid in the 3D printing. They serve as the additional inputs. Vector image is widely used because of its unique advantages. First, vector image is a resolution-independent representation and can be rendered at arbitrary resolution without loss of visual information. Second, compared with raster images, vector images are now more natural and flexible editing because they are built on parameterized shapes like Bezier curves. For example, the left camel with a single hump can be modified to be a double hump camel easily, and we can also thicken its neck. Although vector line drawing is commonly used, it is tedious to manually create. Vectorization approaches are able to produce vector images from the raster drawings directly. However, they tend to take a long time for computation due to the high computational complexity of the optimization process, and they have difficulties in processing sketches with rough textures. In most cases, it is not clean line drawings, but rough sketches that need to be cleaned up and vectorized. Rough sketch simplification methods are able to generate clean line raster drawings, but they require post-processing to convert the resulting line drawings to a vector image. Next, I will introduce our work. We propose a general framework for vector line drawing generation. This framework works with a wide variety of images, such as the clean line drawings, rough sketches, and photographs. Our framework learns to produce vector line art directly, but during training, it depends on raster data only for supervision. In order to process images of arbitrary resolution, we propose a dynamic window mechanism. We also introduce a stroke regularization mechanism to control the simplicity of the output vector images. Next, I will introduce the framework in detail. Our framework takes raster images as input and output the vector stroke parameters. It models a virtual pen surrounded by a dynamic window and generates vector strokes by drawing with the virtual pen. The drawing process consists of four main phases. First, patches from input image and canvas are cropped based on the window. Then, based on the patches, the stroke generator produces the vector parameters. Next, the stroke parameters are approximated into a stroke image through differentiable rendering. Finally, the stroke image is pasted to the last canvas based on the window. Afterwards, the window moves as drawing the stroke. The framework is based on a recurrent model. It draws the next stroke based on the previous canvas in a recurrent manner till the end of drawing. The model is able to move the pen around by sliding to a new position without drawing. Essentially, this is achieved by moving while drawing a stroke and then discarding the stroke. Our model also learns to choose the best window size. For example, when there is no undrawn pixel inside the window, the model is able to enlarge the window to find undrawn pixels and slide there. Afterwards, it shrinks the window and restarts drawing, because a smaller window helps to better draw details. The dynamic window mechanism depends on the cropping and pasting phases. In these two operations, one challenge is that the position and window size are floating numbers instead of discrete values. A straightforward solution is to use quantization, but this leads to misalignment, and the conversion from floating number to integer number causes non-differentiability. To avoid misalignment and discretization and allow for gradient propagation, we propose aligned cropping and differentiable pasting. The main idea is to use bilinear image interpolation. For example, when we need to crop with this window and output a patch of size 2 times 2, we first define the window region into 2 times 2 bins. Inside each bin, we place several sampling points. Value of each sampling point is calculated by bilinear interpolation. For example, for this point, its value is calculated from the values of the 4 corners nearby. This is another example. At last, the average of the values of all sampling points is set to the final value of each bin. Our framework doesn't need vector data for training. This is achieved by differentiable rendering technique. The neural network-based model predicts vector stroke parameters from the input raster image. Then the vector parameters are approximated into a raster image through a neural renderer. Afterwards, the image is compared to the target image to form a raster loss. Given that the neural renderer is fully differentiable, the gradients can be propagated to the stroke parameters. Therefore, this module enables raster-only supervision. During training, we use perceptual loss as the raster loss. This means that we input the rendered image and the target image into a pre-trained VGG16 model separately. Then, we take the output features from different layers. At each layer, we calculate the differences between features from the two images. At last, the perceptual loss is formulated as the summation of all the differences. Another feature of our approach is the stroke regularization mechanism. We know that different vector images can be rendered to the same raster image even when there are short segments and overlap strokes. We are interested in the simplest vector representation, that is, with the fewest parameters. Since we use pen state to indicate whether a stroke is drawn or not, for example 1 for drawing and 0 for moving without drawing, we can make our model learn to use fewer strokes by restricting the number of strokes. So we define a stroke regularization term as the summation of all the pen states, that is the proportion of drawn strokes. Then we add this term to the total loss function during end-to-end training, so that the model can learn to use fewer strokes while producing a better night drawing simultaneously. As a result, the incompact and redundant strokes can be avoided. Next, I will show the results. Our framework works on vectorization task. We compare with two representative vectorization methods. One is fidelity versus simplicity from SIGGRAPH 2016, and the other is polyvectorization from SIGGRAPH 2019. We can see that fidelity versus simplicity fails to draw isolated strokes. Polyvectorization misses small strokes around complex junctions. The computation time is shown under the figures. We can see that our approach is much faster. This is another example. We can see that fidelity versus simplicity produces connected strokes, and polyvectorization has similar artifacts. And they both take longer computation times than ours. Our approach can also be applied to rough sketch simplification task. We compare with some baseline methods. We can see that polyvectorization tends to have low completion when the strokes are lightly drawn. Sketch simplification from SIGGRAPH 2018 is a representative method, but it generates clean night drawings in raster format only. After converting to vector image with polyvectorization, there there also exist artifacts. This is another example. We can also see the artifacts of missing strokes in the two baseline methods. Our framework can also work with photographs like the face images. We compare with two baseline methods and found that our approach generates comparable facial sketches. Then I will show the effectiveness of another important contribution of our work, the stroke regularization mechanism. First, we evaluate its performance on avoiding the redundant or overlap strokes. As can be seen in these results, without regularization, that is, the loss weight lambda equals to 0, the model produces a number of redundant strokes superimposed on the strokes already drawn. After adding regularization, and when the loss weight is 0.1, only 4 overlap strokes are produced. And when with a larger weight 0.2, no overlap strokes is generated. We also evaluate the performance on improving the stroke compactness. In the blue boxes, we can see 4 strokes are produced for that part with model without regularization. 3 strokes are produced when with regularization loss weight 0.05, and 2 strokes when with loss weight 0.2. This result shows that as the stroke regularization weight increases, the model draws with fewer but longer strokes while maintaining reasonably high fidelity. This results in a more compact representation for vector images. Next, I will discuss the limitation of our approach. First, for some highly complicated line drawings like this figure, even when the maximum number of strokes is set to 5,000, our framework may fail to reproduce all the lines, like the missing one in the red boxes. This is mainly because when our CNN encoder downscales the complicated image for global guidance, it might result in the vanishing of thin lines. The potential solutions to this issue can be chaining with higher resolution images or using alternative methods to better encode the global guidance. Another limitation is that it is still difficult for our framework to generalize well on complex rough sketches or photographs, and it may produce artifacts in some results. For example, in rough sketch simplification, the output lines in our result are not as smooth as those from sketch simplification. In the face image to line drawing, the nose in our result is connected with the eyebrows, while they are clearly separated in result from photo sketching. To improve the performance, combining the pixel-level sketch simplification or image-to-sketch model and our approach in a single end-to-end model can be a promising future direction. The last issue is that our framework tends to generate incorrect topology or stroke order in some types of junctions. For example, in the two black boxes, most people would draw the horizontal curves from left to right or the opposite instead of drawing a sharp turn. However, our model is not intended for recovery of topology or meaningful drawing order. While correct topology and specific drawing orders might be beneficial for certain applications, we can incorporate post-processing or predefined principles as constrained information to form a future extension of our approach. At last, I will have a conclusion of my presentation. Given that vector line drawing is fundamental in the field of graphic design, we introduce a general vector line drawing generation framework that works with a diversity of image types. The drawing process is achieved by our proposed dynamic window mechanism so that our framework is able to process images of arbitrary resolution. We also introduce a stroke regularization mechanism to control the simplicity of the output vector images. Last but not least, We have released the code and the trained models, and the links are here. Thank you.